Today we will read a new type of flowchart to implement the digital hardware called the Algorithmic State Machines Chart, or simply ASM Chart. So, first we see what is ASM, what do we mean by Algorithmic State Machine Chart. Now, before that we recapitulate the synchronous sequential design. The synchronous circuit normally it is made up of a combinational circuit with the memory, and the memory is a clocked flip-flops. Now, the performance of synchronous sequential circuit, or simply we can tell the state machine, can be represented by a state diagram. Now, this performance can also be represented by a flow chart, a systematic way. A flow chart is a way of showing actions and control flow for a computer program which is translated into software. Now, similarly, like using the flow chart, or what do we mean by software flow chart, the performance of synchronous sequential machine can also be represented by a flow chart, and this is called the algorithmic state machine chart. So, again it is a flow chart. We can tell that this is a hardware flow chart. So, an algorithmic state machine is simply a flow chart like way to specify state diagrams for sequential logic which is used to implement hardware. So, while flowcharts typically do not specify time, an ASM explicitly specifies a sequence of actions and their timing relationships. So, what we can tell that ASM, this is the basic definition of ASM. This is in broad sense, this is a hardware flowchart, and the difference from our normal software flowchart, that our software flowchart does not specify time. So, does not specify time, whereas the ASM explicitly specified a sequence of operations. So, this is the difference from a software flowchart or the normal flowchart from the ASM. Now, normally ASM, just like our normal flowchart, ASM have some symbols. So, an ASM chart specifies the sequence of operations along with the conditions required for their execution. So, here the ASM is used to design a digital system. Now, for the problem or for the whole digital system design, there are the sequence of operations, and this ASM chart specifies this sequence of operations. Now, normally three symbols are used to develop the ASM chart. One is called the state symbol, then the conditional symbol and the decision symbols. So, here only three symbols are used for ASM flowchart or ASM chart. Now, state symbol is a rectangular box marked with the symbolic state name containing register transfers and output signals activated when the control unit is in the state. So, this is a rectangular type of box. Normally, it has some name and some binary coded value is given to the box. Second is the conditional symbol. Normally, this is a this is a oval shaped output box with entry from a decision block and outputs activated from the decision conditions being satisfied. So, normally it is a decisional execution, or if the condition is satisfied, then this decision should be taken. So, this conditional symbol is a oval shaped output box. Now, the third, the decision symbol is a diamond box that describes its effects of a specific input condition on the control. That means, if this condition is satisfied, then this decision is taken, means this operation should be executed. So, it has one input path and two exit paths, one for true as it is a decision. So, one for true and another for false. Sometimes it is a hexagon that describes one input path up to 2 to the power n exit paths, or more than one, a bus input and a bus output, we can tell. So, these decision symbols, normally it is a diamond shaped, but sometimes it can be a hexagonal. So, these are the three symbols, the state symbols, the conditional symbols and the decision symbols are being used to represent a ASM chart. Now, first we see the state symbol. It is a rectangular shaped. Now, here the one state name should be there, and the binary code assignment, say if it is a 4 bit, say 0010, this type of binary code is assigned here. It has one entry and one exit. Normally this is the state output. So, it is a rectangle with the symbolic name for the state marked outside the upper left top. So, state name, or we can call the symbolic name of the state, or sometimes we can call the logical name, symbolic name of the state. The convention is, normally this name is written on the left top. Now, it contains register transfer operations and outputs activated within or while leaving the state, and that is the exit point. So, this is the exit. An optional state code if assigned outside the upper right top. So, this is a binary coded assignment. This is a binary coded assignments. So, this is a logical name, and when it is assigned to binary, just like our state diagram, so it is given to the binary coded assignment. So, this is our state symbol. Then the second one, the conditional symbol. It is a oval shaped box, one input path from a decision box or decision boxes. So, entry is the input, this is the input path, this is the output path. And this is a conditional. So, register transfers or outputs that occur only if the conditional path to the box is taken. So, these are my initial is the output variables, that means if it is a condition to be checked, that is the value of the output variable that is there. So, this is my conditional symbol. Now, the third is the decision symbol. Normally, it is a diamond shaped box. Sometimes this can be a hexagon. So, this is one input path, the entry point, one input condition placed in the center of the box that is tested because it is a decision, a true exit path taken if the condition is true. As it is a decision, so if it is true, the condition is true, then it follows a path normally called the true path. If the condition fails, then it follows a different path, normally it is called a false path. So, that is the condition is false, a false exit path. So, there are one entry point, two exit point. Now, symbol is here this is the entry, one entry point, this is the one entry point, and there are two exit. So, this is the, if the condition is false, then this is one exit 1. If the condition is true, then it is a exit 2. So, there are two exit point. Sometimes another decision symbol is used, that is a hexagon. Normally another type of ASM decision symbol is hexagon. Normally one again here one entry point, and two exit point. This is the condition. If it is false, then 0. If it is 1, means true. So, this is the entry point, and there are two exit point. So, normally these are the three symbols, ASM symbols are used to represent the ASM chart. Now, what are the similarities between ASM chart and a state diagram? So, each state in a state diagram is basically similar to state symbol. What we have seen, the state symbol has also a name, just like our state diagram, a logical name is there. So, state in state diagram is nothing but the state symbol, and the decision symbol is similar to the binary information written on the lines connecting two states in the state diagram. So, decision symbol is the binary informations. Normally, that what output it will generate, what will be the value, that will be the what value it will transfer. So, that information written on the lines connecting two states in the state diagram, that is nothing but our decision symbols in a ASM chart. So, these are the similarities. Now, this is a simple example that how the one ASM chart can be constructed using the three type of symbols. So, here we have taken one state symbols. Here this is one state symbol, one entry point is here. So, this is one state symbol. Now, this one is a decision symbol. This is a decision symbol. If it is false, if say the decision symbol is written as a say x1, the value. If it is false, then it is the entry point of another decision symbols, say called x2. Again, if it is false, then it goes to the conditional output symbol, and this is the conditional output symbol, the oval shaped, where the output variables are say x4 and x5. Say the output variables are here say x4 and x5, and this is it has one exit path. So, this path we have considered only the left path, means false path. We have checked the false path. Okay, as if this is the false path. Now, again if we consider that the entry path, from the entry path to the first conditional symbol, and if it is now if it is true, then it will follow the true path or another exit point 2, it will directly goes to a conditional symbol. So, this is one conditional symbol, and it has one exit point. It has one exit point, and it goes to say a decision symbol called x3. Now, again if it is false, then another exit path it follows. If it is true, then another exit path 3. So, we can tell, say if we see that how many exit paths are there for this ASM charts. Say we have seen a false path. So, if it is a false path, then this is only one exit path. This is one exit path 1. This is one exit 1. This is a exit 1. Now, if we consider the true path, then this is first it is a true path, then this is a conditional symbol, it has only one exit path. Now, it goes to a decisional symbol. So, it has two exit path, one false. So, we call this is the exit 2. This is the exit 2. This is another exit point. Now, if it is a true, it was coming like that, then it is a false path, it follows exit 2, and if it is a true path, so then the total true it will go to a exit path 3. So, this is one exit 3. So, there are there are 3 exit paths of this ASM chart. So, normally in this way the design is represented by a special type of flowchart consisting of 3 type of symbols: the state symbols, the decision symbols and the conditional symbols, and these are called this is one example of the ASM connected symbols, or we can tell that this is the ASM chart, one example of the ASM chart. Now, some correct and incorrect ASMs. Say here just arbitrary we have taken some ASM charts consisting of 2 type of symbols only. So, this is one state symbol, say this is the logical name is X, or say the name is, this is the state symbol, so this is a state symbol, and it has one, say X. Now, one entry point and one exit point. So, it has one entry point and one exit point. Now, it fits to a decision symbol. So, it goes to a decision symbol, this is a decision symbol. Now, say if it is false, then it cannot fit the same point. This is a incorrect ASMs. This path is correct. If it is true, the true path, then it is a exit point and it goes to another state symbol. It goes to another state symbol, say Y. So, this is Y. So, this path is correct. So, what we can tell, this path is correct, but this is incorrect. So, this is a incorrect, symbols are correct, but the connections are incorrect, and so the ASM chart is incorrect. So, this exit point cannot be the same entry point. The problem is here the exit point and entry point are the same. So, if we remove this mistake, what will be, this is my exit 1. So, this is one exit 1, and that means if this is a false, if this condition is false, then it should go to a state symbol. Always it should go to the input of a state symbol. So, this is one entry point. This is one entry point. So, here the same line cannot be the exit or the entry and exit. Here this is a two different thing, one entry point, and now this exit goes to there, and the remaining portions are same. So, this is a correct one, and this is called the correct ASM chart. Now, we take one example of an ASM chart for a 3-bit counter. So, for a 3-bit counter, this is a mod 8. So, it has 2 to the power 3 states, 8 states. If the state symbols or the logical name is ABC, the 3 things, then actually that it will be 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, like that it will goes to 1, 1, 1. Now, before that, that means the input should be like, here the input will be that first it will go to a say state symbol, say state symbol, say this is ABC and code is 000. So, it has one entry point, this is my initial thing. Now, it has one exit point, and now I am putting here one decision symbol, say called say decision symbol D. Now, if D is false, means if it is a 0, if it is false, then again it should go to the, again it will start, or it will be in the initial state only. If it is 1, that means this is another exit point, then only it will go to the next state or the other state symbol coded as 001. So, if now we think that, say we can give a different value, different name, say this is a initial state small a, this is small b, and then it will, so this is a true path, and now as it is a state symbol, it will continue, like that. So, the remaining portions, these are drawn here. So, before actually at the input of this first state symbol, here this it will be added. That means one state's initial state symbol followed by a decision symbol, and if it is 0, then again it will stay in the same state, means initial state, and when it will proceed or it starts counting when it is a true. So, actually this is the exit point, or the, if this is true or condition is true, or this is the exit one, then it starts counting, and in that way we can represent the ASM chart. Now, before giving the general methodology for the state machine design, we take another arbitrary example, that how actually the timing specification is represented by ASM chart, because that is the basic difference from our normal flowchart, or what we call the flowchart to implement the software program. So, we take one example of an arbitrary ASM chart. Say we are taking a symbol register X. Say we have a register X. There are 3 states. T0, T1 and T2. The machine is such, or the synchronous sequential machine that we want to design, that is such that during T0 x is cleared, means set to, it is reset or cleared or set to 0, and a flip flop A is checked. Now, if A equal to 0, then the next state is T1. If A equal to 1, x is incremented by 1, that means the circuit increments the value of the register x, because x is a register, x by 1. So, x is incremented by 1, and the next state is T2. Next state is T2. So, this is the a simple machine specification. So, we have 3 states T0, T1, T2, and the conditions are this: if A equal to 0, next state is T1, if A equal to 1, x is incremented by 1, and next state is T2. So, if we draw the ASM chart, so first that one state symbol and the register x is given. So, this is the states at T0. As it is a state symbol, it has one entry point and one exit point. Now, it will go to a decision symbol, and the decision symbol is A is checked. So, the flip flop A is checked. So, the variable is placed inside the diamond box. Now, we know that diamond box has 2 exit point. Then if A is 0, that means if this is a false path, it should go to the state symbol T1. If it is 1, if A equal to 1, what we have, that x is incremented by 1. That means now we need a oval shaped, means our conditional symbol. So, x is incremented by 1, that means x is x plus 1, and now it goes to another state symbol called, state name is T2, and this is T2. So, now if we give a binary code, say we have 3 states T0, T1, T2. So, we need 2 bit to represent the 2 binary code. So, if it is a, say it is a 0 0, this is a T0 0 0, then T1 is 0 1 and T2 is 1 0. So, this is my ASM chart of an arbitrary a simple state machine. Now, what will be the state diagram for this ASM chart? The state diagram will be like the initial state T0 coded with 0, then it will go to a 0 1 means T1 if it is false path, if it is a true path then it will be a T2 1, that means it is 0 0 0 1 1 0. So, this is the state diagram of the ASM. And the operations to be performed during the state T0, that will be there will be 3 operations. One will be clear register X, check the flip flop A for 1 or 0. If 1, that means if A equal to 1, increment X by 1. Okay. So, we have seen that how from the machine specification how the ASM chart can be drawn, and from there the state diagram can also be come out from that ASM chart. Now, we see that what are the generic steps for the state machine design using the ASM chart. Normally, this is a 3-step procedure. The first step is draw the ASM chart from problem definition. Problem definition means just now that machine specification I told, that one register X is there, a flip flop A is checked. If it is 0, then go to a state T1. If it is 1, then increment X by 1, and the next state will be T2. So, this is my problem definition or the problem specification. So, from there just now we have seen how the ASM chart can be drawn. Second step is derive the state transition table representing the sequence of operations to be performed. So, now the state transition table representing the sequence of operations to be performed. That means, the list of operations to be performed to execute the machine, we have to derive that thing. Step 3, derive the logic equations and draw the hardware schematic. So, once the logic equations are derived, we know that the hardware schematic can be drawn. Now, the hardware can be designed using either classical sequential design or PLS, or what we have discussed in details this portion, that how the hardware is designed, or given a set of logic equations, how the hardware can be implemented. So, mainly these are the 3 basic steps of the design of state machine using ASM chart. Now we see one example, the design of a 2-bit counter using ASM chart. So, first the problem specification. Example is 2-bit counter which counts the sequence 00, 01, 10, 11, 2-bit counter. Now, what are the design specs? If the count is XY, say we represent our convention is MSB is X, or MSB is X and LSB is Y. The system starts with an initial count of 3. A start signal 1 initiates a sequence of operations. That means as if this is just like a, this is a switch, this is just like a switch. If I equal to 0, system is in initial state T0 with count of 3. If I equal to 1, it starts the sequence. Now, some more specs, that when I equal to 1, counter Z is first cleared to 0, system moves to state T1. In this state, Z is incremented by 1 at the leading edge of each clock pulse. When the counter reaches 3, it goes back to T0, because so it will be all the time it will be 0 0. If it only it counts 1 and 2, that it will change 0 1 1 0. Again when it will be 1 1, it goes back. The process continues depending on the status of the start switch 1. The counter output will be displayed on a 7 segment display, and a LED is connected at the output of flip flop W. It will turn on for the count sequence 1 2 by clearing the flip flop W to 0. So these are my, this is the design or the problem specs what I have to design. A 2-bit counter, I want to see the performance or the function of the counter in this way. Now, the first step, it is a 3-step procedure. So, first step is draw the ASM chart. The system is in initial state T0 and waits for start signal to become high. Now, if I equal to 1, it clears, that means if it is a 1, it clears counter Z and the system goes to T1. Counter is incremented at the leading edge of clock pulse. In state T1, one of the following two operations occurs. If Z is 1 or 2, flip flop W is cleared to 0 and control stays in state T1. If Z counts to 3, system goes back to T0, because it is a only a 2-bit counter. So, the ASM chart, just from the problem specification, if we derive the ASM chart or draw the ASM chart, so it is a, say this is the initial state. Now, this is my switch. We can think that as if this is my switch. If it is 0, always it stays in the same state. Same state. So, this is the state symbol. If it is high, that means 1, then only it will proceed. Proceed means Z is cleared. So, this is my conditional symbol that Z is cleared to 0. This is the conditional symbol. Now, it has one entry point, one exit point. Now, Z is in at each leading edge or positive edge of the clock pulse, it will be incremented. So, Z becomes Z plus 1. So, this is my state symbol. This is one state symbol. Now, again it goes to a decision symbols, that if y is 0, that means if it is a false, then the flip flop W is cleared to 0 and again goes back to, that means it continues, Z is Z plus 1. If it is y is 1, then it comes to another decision symbol, and if it is 0, then only W flip flop W is 0 and again it goes to the state T1. It goes to state T1. So, for this is for 1 and 2 count, it is in the state T1. Now, if it is x is 1, that means it is a 2-bit counter. So, if it counts 3, so again it goes back to the initial state. So, this is my ASM chart. So, mainly from the problem specification or the problem definition, the ASM chart is drawn accordingly. Only one thing is to be noted, that here a timing specification is always maintained by the ASM chart, which is totally absent in our normal flow chart. There is no timing specification, but here always the timing specification is there. Now, the second step is the derive the state transition table representing the sequence of operations. So, the state transition table, we see that the counter, then it is the W flip flop, the conditions, and then what will be the state. So, if it is 0 0, the flip flop value is 1, conditions to be checked is 0 0 and state is T0. If it is 0 1, then that means it is 1, then it will be in T1 state. If it is 2, then it will be in T1 state. Just now we have seen. See, this is the two things. If it is 1, that means y0 and another is that y1 x0. So, this is 1 2, both the conditions it will be in state T1. It will be in state T1. Now, when it is 1 1 counter value, then the W, the flip flop W is 1 and again it goes back to the initial state T0. So, again it will be T0. So, initially at T0, then it proceeds, it is T1, T2, that means for count value 1, 2, again when it will be 3, it goes back to the initial state. So, these are the 4 states to be counted. Now, the third step is derive the logic equations and draw the hardware. System is divided into 2 sections, the data processor and controller. So, the data processor, the requirements for the design of data processor are defined inside the state and conditional boxes. And typically these data processors are implemented by the digital components like registers, counters, multiplexers and adders, etc. So, here also we will be seeing that the hardware part, that is normally the system is divided into 2 and the data processor will be implemented by these registers, counters, multiplexers, adders, etc. We will be seeing later. And then the controller, the logic for the controllers is determined from the decision boxes and the necessary state transitions. this is the hardware schematic for a 2-bit counter. Just now what we have seen, see it has two parts, the controller part and the data processing part. What we have seen, that if we draw that it has two part, one is the controller, another is the data processing, another is the data processor. The inputs are here and after processing the output. So, actually there will be a partition here. Now, for this particular example of 2-bit counter, the data processor part is the 2-bit counter, this is the 2-bit counter, say the 2 input AND gate, the flip flop W, these 3 constitutes the data processor parts. So, these are my data processor, these are the data processor part. These 3 are the data processor and the controller is there. So, the input is coming, see the input, these are my inputs x, y to the controller. From here that partition is there, this is the data processor and this is for the output, that to a 7 segment decoder display, this is only for the counter value, checking the counter value. Now, if we see the state table for the controller design, then there will be present state for controller, CONTL means controller and COUNT means counter. So, present state controller, present state counter, inputs controller, next state counter and next output states. So, present state controller, the initially it will be the T0 state, initially it will be T0 state, the present counter value is 1 1 and the inputs coming is 0 1 1, 0 means it will stay in the same state. So, the next state is again 1 1 and the next output states of the controller is T10, T01. Now, when only that I equal to 1, it will be changed. So, the T0 xy is 1 1 1 1 and then only the next state is changed to 0 0 and T1 becomes 0, T0 is 1. Now, in this way similarly the as I described now, that it is when it is T0 xy is 0 0, again it is a 0. So, it is 1 0, in this way it will the state table can be formed. So, if we see the hardware schematic, that means that the controller part we can design and then the data processing part, in this way the 2-bit counter with the flip flop, that the state tables we can derive and accordingly the state tables can be implemented by the logic. Once we get the tables, we can logic equations we can get from the state tables and then the equations can be implemented by classical techniques or by PLS. So, in this way any type of, we have seen one small examples of design of a 2-bit counter, that any type of digital systems that we can design using the ASM chart. Now you see that today's lecture quiz, the lecture 32 quiz. Mainly today we have read the algorithmic state machine chart for designing the digital systems. So what is an ASM chart? How does it differ from a normal flowchart? Here the flowchart means this is a normal flowchart, or normally the flowchart for the software. Then state the basic steps of state machine design using the ASM chart. And today we have discussed the design of a 2-bit counter, and similarly we can design any machine, say a modulo 8 counter or 3-bit counter, and the quiz 3 is draw the ASM chart for a 2-bit multiplier. So the 3 basic steps, the drawing ASM chart, derive the logic equations, and from there the hardware implementation we have to do for a 2-bit multiplier. Today we will start discussion on the design of computer instruction set and the CPU. First we will see how we can design the computer instructions. Now before starting the design, what do we mean by computer instruction? All of you know that a software program consists of a sequence of instructions. Now an instruction performs on stored data. That means a program is nothing but a sequence of operations to be performed on the data, and an instruction is one single operation on the data. So an instruction has two components. Normally we call the opcode field and the address field. Now opcode field defines the type of operation and it operates on the stored data. Address field contain one or more addresses of data on which the operation is to be performed, and data may be stored in a microprocessor register or in the main memory. So instruction has two fields, opcode field and the address field. So when we want to design a computer instruction or to represent